So the Josephus problem comes from Flavius Josephus and his 40 soldiers that were trapped in a cave by Roman soldiers. Instead of committing suicide because they didn't want to be captured, they chose to kill each other by casting lots because murder is a repentable sin and suicide was not. Josephus didn't want to die, and so the problem kind of originates with what spot does Josephus stand in so that he isn't executed and he's the last one left alive. The Josephus problem that we're concerned about is a theoretical counting game. The standard approach is that a group of people stand in a circle waiting to be executed. Counting starts at a predetermined point and goes in a predetermined direction. And you skip a certain number of people ranging from 2 to K, and after that many people is skipped, the next person is executed. This process repeats itself until there is only one person left, and the goal is to pick the spot in the circle that avoids being executed so that you survive and everyone else dies. So we generated our little circle diagram with a for loop that just did some trig and positioned them evenly apart based on the number that was selected with the slider. It was kind of a fun little second algorithm that I really liked.
The image on the left is a close-up of our dashboard. From top to bottom we have a title label, the current number of people label, our input slider, our anime button, and our prediction label. One thing that we discussed as a group when programming this application was that we wanted to prevent the user from giving the program bad input. After a little bit of research, we decided that a slider was probably our best bet. Making a slider was great for this project because we could hardcode a set range of values that the user could enter. The only real adjustment we had to make was to make sure that we got an integer from the slider. Sliders in JavaFX have doubles as their default values, so we had to make sure to cast the current value of the slider to an int to make sure that the values were in the right format. Our slider actually controls quite a few things for our GUI. As you drag the slider, it will update the people in circle label with integer values. When you release the slider, the circles are redrawn and our prediction algorithm is run. A prediction is calculated to determine who the survivor will be, and then that value is then placed into our prediction label. Last, we have the animation button. When this is pressed, our Josephus algorithm is ran to determine who the winner actually is. When this calculation has been completed, each of the circle's images is changed to its killed image, except for the survivor. The picture on this slide is a close-up of our animation area. As stated in the previous slide, each time the slider is released, the circles are redrawn. This is first done by clearing all of the previous circles from our pane and starting again. First, the large gray circle is drawn. Then, to draw the people, we access the current value of the slider to determine how many people needed to be added to our GUI. By providing a few values to a circle algorithm, each person is given an x and a y coordinate that is equally distant around the gray circle. After the values are assigned, the person is drawn onto the pane. We follow the same pattern to place labels over each person to number them.
When the number of chairs is a power of 2, the winning chair will always be 1. If you think about it, in the first round, all even numbers will be killed off. In the example of 8, this means 2, 4, 6, and 8 will die, and it's 1's turn again. This means that 1, 3, 5, and 7 chairs are left. Since we're starting with 1 again, these can be renumbered to 1, 2, 3, and 4, which again is a power of 2. Killing off the evens, we get 1 and 3, which can be renamed once again, so 1 kills 2 and 1 is the winner. This means that whatever position starts when we are left with a power of 2 will be the winning chair. Using this idea, we can rewrite n as 2 to the power of something plus something else, or 2 to the a plus w. Since every other chair will be killed, w will equal 2 times how many steps we've taken plus 1. Using the original Josephus problem's value of n equals 41, let's try this out. The largest power of 2 is 32. So 41 equals 32 plus 9, meaning there are 9 steps until we found our winner. 9 times 2 is 18, plus 1 is 19, so the winning chair should be spot 19. Since we're using a power of 2, we should think of binary. We can use the binary representation of n to solve this problem too, which brings us to the prediction algorithm that we used in our program. First, we have to convert n into its binary representation. In order for this algorithm to work, the leading bit must be a 1. For example, 3 will be written as 1, 1, not 0, 1, 1. Then we use our most significant bit. If you remember from the last example, this was our 2 to the a. Now we move this bit, which should be a 1, to the end of the binary string, so now it is the least significant bit. This does a couple of things. First, it subtracts the largest power of 2. What is left of the string should be the number of steps to the winning chair. Second, the remaining bits are shifted up, which multiplies it by 2. Finally, moving the 1 to the last spot adds 1 to the string. So we are left with 2 times the number of steps plus 1, just like in our last slide. Converting this back to decimal, we have 19, just as before. For our program, we created a function for each step. 1 to convert a number to a Boolean array, 2 to swap the most significant bit, and 3 to convert back to decimal. Since we designed our program to work with an array, it's not very easy to go around a circle killing every other one, because the last spot in the array cannot see the first. In the example of n equals 10, 0 kills the next spot, 1, 2 kills the next spot, 3, and so on, killing all odd numbers until we reach the end of the array. It should be 0's turn again. The next round, with n equals 5, 0 kills the next spot, 2, 4 kills the next spot, 6, but 8 doesn't have a next spot, so who does 8 kill? Looking at it in a circle, it's obvious that 8 should kill 0. However, in the scope of an array, and in the scope of our program, 8 doesn't think there's anything after it, but we don't want to skip 8's turn. To solve this issue, we made the Josephus algorithm recursive, passing in a myTurn index to indicate who needs to go first. Since the myTurn index of this iteration is not 0, this means that it's the last person's turn, and they are about to kill spot 0. Afterwards, we will continue as usual. 4 kills the next spot, 8. In our next iteration, n is 1, so we have found our winner. Our final algorithm can be separated into 5 simple sections. Step 1 is our base case. If n equals 1, then we have a winner. Return that person. Step 2. If the myTurn index is 0, simply iterate through the array of people. Each will ask, am I alive? If not, skip my turn. If I am alive, I'll ask, is there someone after me? If so, kill them. If not, remember that it's my turn. Step 3. If the myTurn index is not 0, kill spot 0. Then iterate through the rest of the array as normal. Step 4. Make an array of only those that are alive. This is the same as renaming our circle like we talked about before. Step 5. Call the Josephus algorithm again, passing in our new lineup of people and whose turn it is. This will manually go through an array, killing every other person until 1 remains.
So this is our GUI demo. Over here we have the slider. This allows you to alter the number of people in the circle. And below run animation, we have our prediction, which the Josephus algorithm will predict the winner will be. We wanted it to kind of be slow and iterate through and kill each person one at a time, but we found that trying to get that to sync up properly with all the moving parts and as we were trying to redraw all the circles was kind of too much of a headache. Had we had more time, we would have liked to do it, but we just didn't get there.